In this video, we're going to talk about free fall, and hopefully at the end of it, you'll have a good understanding of what free fall is. So, as far as the definition of free fall, is any object that is only under the influence of gravity. Now, what that means is gravity is the only force that is acting on the object. And anytime that gravity is the only force acting on the object, that means the object is going to be accelerating or speeding up. And whenever an object is falling, it has a very specific acceleration, especially on Earth, has a very specific acceleration due to gravity. And we use the letter G to represent that acceleration due to gravity. And our acceleration due to gravity with objects on Earth is negative 9.8 meters per second squared. Now, what does this negative 9.8 meters per second squared actually mean? That means that every second the object falls, it gains a velocity of 9.8 meters per second. And the only reason there's a negative sign in there is to represent the downward direction. That means the object is falling down. The negative sign just gives you the direction. It doesn't mean anything bad or negative, although it is a negative sign, but it just means direction, downwards. So hopefully I could draw a little picture over here and help explain what's going on. So we have our guy over here, and he's standing on top of a tall building, we'll say. And he has an object that he drops off the building. Now, the moment that he drops that object, it's moving at a velocity of 0 meters per second. So we're going to call this V0, V0 or V naught for initial velocity. Oops, made a little mark there. So this object, the moment it's released, is moving at 0 meters per second. But we know as it falls, it's going to start moving faster and faster. So after 1 second, it's going to be moving at negative 9.8 meters per second. That means after 1 second, and we're going to put a little V1 right there to represent 1 second. That means it's moving at negative 9.8 meters per second. That just means it's the negative sign, once again, just means it's moving downwards. But after the next second, so we'll say this is V2 for 2 seconds. At this point, it'll be moving 9.8 meters per second faster than what it was here. So originally, it was going 9.8 meters per second. But at the second, it's going to have gained 9.8 meters per second. That means if you add 9.8 to it, after 2 seconds, it is now going 19.6 meters per second. And then if it were to fall a third second, we'll say V3. At that point, it would have gained another 9.8 meters per second. So plus 9.8 means now it's going 29.4 meters per second. Let's throw one more out there. At this point, all the way down here at V4, we're going to add another 9.8 to that, because it gained another 9.8 meters per second. So now down here, all the way down at the bottom, it's now going 39.2 meters per second. So it started off at 0. That moment that I released it, it was going 0 meters per second. And then after 1 second, it was going negative 9.8 meters per second. And then the next second, I forgot my negative signs, it was going negative 19.6 meters per second. And then the next second, forgot my negative sign again, now it's going 29.4 meters per second, and then finally it gained another 9.8 meters per second. So it was increasing its velocity as it fell. It was just going faster and faster and faster. And once again, that negative sign just means it's falling downwards. Doesn't mean it's slowing down. It just means it's going in the negative direction. So as the object was falling, it was increasing its velocity. And you notice it was actually increasing the amount of distance that it covered every second. So this first second only covered this little distance right here. The next second, it covered this big distance right here. And then the third second, it covered even longer distance, and fourth second, even covered even a greater distance. So every second was covering a greater and greater distance. So every object on Earth should fall at a rate of negative 9.8 meters per second squared. Now you might be thinking, well, wait a minute. I know not everything falls at the same rate. And on Earth, you're exactly right. Let's say we have a hammer and a feather. Wonderful drawings. I know you're thinking the same thing. Now let me ask you this question right here. If I were to drop a hammer and a feather, which one would hit the ground first? Now hopefully you all have had the experience in your life to know that the hammer would definitely hit the ground first if I were to drop both of these at the same time. Okay? So, hammer hits the ground first. But why is that? What is happening between these two objects to where one of them falls faster than the other? But up here, I said that everything should accelerate at a rate of negative 9.8 meters per second squared. Everything on Earth should fall with this pattern. But that's not true. We know the hammer would hit the ground before the feather. And the reason why that would happen is a little thing we like to call air resistance. Typically, in all of our equations that we're going to work with, we are going to ignore air resistance. Ignoring air resistance makes our life so much easier. Makes everything make more sense, and it makes our equations, our favorite kinematic equations here, it makes them all work out with these accelerations. Because we know that a hammer will just cut straight through the air a lot easier than the feather will. The hammer kind of falls and gets faster and faster, as the feather over here, it kind of would start to float and just kind of slowly go to the ground. So if we ignore air resistance, then every object on Earth should fall and hit the ground at the same time. If you actually look up the video of the astronauts on the moon, they did a feather and hammer drop, and they found out which one would hit the ground first because the moon has no air. And they dropped them both and found out that they both hit at the same time. So if we take air resistance out, all of our kinematic equations work and everything on Earth should fall at this rate. So let's look at an example and see how we can use our kinematic equations to figure out something about an object when it is in free fall. So I got this question right here I want us to ask. All right, so we got a person over here, and they're standing on a cliff, and they want to know how tall is the cliff. This is what they're trying to figure out. And it looks like they're in some sort of desert setting. And they go to the edge of the cliff and drop a rock. And they measure that it takes 2.4 seconds for this object to go from here all the way down to the ground. And we only have the time it takes for the object to fall and hit the ground. And we need to figure out how tall the cliff is. Well, there's only one piece of information given to us, but that's because all the other information is stuff that we know. So let's start off by making our list of other things that we know. We also know the initial velocity of the object, right? Just like whenever this person over here, whenever they drop something, the initial velocity was 0 meters per second. So we're going to say our initial velocity is 0 meters per second. We also know the acceleration due to gravity. So we could say A, or we could say G, is negative 9.8 meters per second squared. Because we're going to assume this person just found some sort of rock. A rock is not really affected by air resistance that much, so it falls pretty much at the rate of negative 9.8 meters per second squared. So I'm going to just kind of write that up here. Our acceleration is equal to g, which is equal to negative 9.8 meters per second squared. And what are we trying to solve for? Well, we're trying to find the distance. I'm just going to write a D with a little question mark here. And now I need to go to my kinematic equations and figure out which equation I can use to solve for distance here. Now, we have our acceleration. We have our initial velocity. Here I wrote V0. VI means the same thing. And then we have our distance. We're trying to figure out how tall the cliff is. And then we know the time. That was the thing that we measured whenever he's dropped it. He probably started a stopwatch and then stopped it once it hit the ground. Found out it was 2.4 seconds. So which one of our equations over here would solve our problem? And if you looked at it and you said this one right here, you would be so right. So let's go ahead and write down that equation and see if we can solve this problem. So we're going to say distance equals VI t plus 1/2 AT squared. Now, the reason why I used this equation here and not the other ones is because all the other equations had information that I couldn't use, or it would leave me with too many question marks, such as this one right here. I couldn't use this one because it has a final velocity, and we don't know anything about final velocity, nor are we looking for it, and we're also trying to find time. This equation, we're trying to find distance. This equation over here doesn't say anything about distance in it, so we can't use that one. Same reason we can't use this one, because we're trying to find distance. This equation doesn't even have distance in it, so that's useless to us. This one down here, it does have distance in it, but the reason why we can't use it is because it has this final velocity over here, and it doesn't take into account time. So that's why we couldn't use this one. But this equation over here, it does work because it has distance, initial velocity, time, and acceleration. It has everything we need. So, I have my equation written down, and I'm just going to go in and plug in my numbers and try to figure out how tall is this cliff. Well, we're trying to find D, so I'm going to leave that as the letter D. Our initial velocity was 0. Our time was 2.4. And we have 1/2. And then for our acceleration, negative 9.8. And then our time, once again, 2.4, and we're going to square that. This part right here, 0 times 2.4, that's 0. I'm not even going to bother keeping writing it down because it's just going to be a waste of time. So distance equals, we have 1/2 times negative 9.8 times 2.4 squared. So let's go ahead and plug this 1/2 times negative 9.8. So let's see here. 1/2 is also 0.5 times 9.8, throw the negative sign in after that, negative 4.9. So we have negative 4.9, and we're going to multiply that by 2.4 squared. So let's do this. 2.4, and then we're going to square that, 5.76. So multiply that by 5.76, and let's multiply those two numbers together. We are almost there. Times 4.9, negative 28.224. I'm just going to go 2 decimal points into that. So our distance is negative 28.22, and the units for distance would be meters. So therefore, that is our answer. So how tall is the cliff? Well, I say negative 28.22 meters. That's because it fell 28.22 meters down. That negative side, once again, just means it's going down. So if we're really going to answer the question, the cliff is 28.2 meters tall. But yeah, all the math works out just using our kinematic equations and our basic understanding of how things fall, and we can understand and figure out how tall things are just by using one measurement of time. Pretty interesting stuff.